Now we can talk about some primes. So we have a definition. Number one, which says that an integer p greater than 1 is called prime. The following, if the only divisors of p are, if the only divisors of p are plus minus 1 and plus minus p. Number two, two integers x and y are called relative prime or relatively prime if their GCD is 1. Now we have a theorem which says for two integers gives us necessary and sufficient condition to be relatively prime. So theorem (11), let x and y be integers and non-zero. Integers, then x and y are relatively prime if and only if there exists s comma t inside Z such that 1 is equals to sx plus ty. Can prove this. Can prove this. Say let x and y be relatively prime then GCD of x comma y is 1. And by the theorem 1.2.8, there exist integers x comma t, s comma t, such that 1 is sx plus ty. So these are the straightforward conditions. Now conversely, suppose one is Sx plus Ty for some pair of integers s comma t, let d is GCD of x comma y. That means d will divide x and d will divide y, and so does d will divide Sx plus Ty. Or d will divide the 1. Now, since d is a positive integer and d divides 1, then d is 1. Thus, GCD of x comma y is 1. So x and y are relatively prime. Perfect. We have another theorem, says something similar, but quite important. We have 3 integers now, x, y, z, with the condition that x is non-zero, is not 0, if x divide the product of y, z, and x comma y are relatively prime, then x also divides the z. You can prove this. This is a simple one. So let's say since x and y are relatively prime, there exist s comma t inside the integers such that 1 is Sx plus Ty. Then by the previous theorem, by theorem 1.2.11, we have z is Sxz plus Tyz. Right? We just have to multiply z with both sides of this equation. And now x divides x, and by hypothesis, x divides yz. Thus, x divides Sxz plus Tyz, and so x divides z. We also have a corollary for this theorem. Let's say we have integers x, y, p with p is a prime, if p divides the product of xy, then either p divides x or p divides y. It can't be, it can be like that. We have another corollary that late we have x1, x2 up to xn comma p inside the integers with p a prime if p divides their product, p divides the product, then p must have divide one of them. For some I, where I is between 1 and n. And now we will give the most important theorem of this part, which is this is fundamental theorem of arithmetic. Arithmetic says that any integer n greater than 1 has a unique factorization up to order that n can be written as p1 power e1, p2 power e2, product up to ps power es. This is 1.1, where p1, p2 up to ps are different or distant primes, and e1, e2 up to es are positive integers. I can prove this using the previous information, but that would be a very long lecture. So we will just skip this and talk about some of the corollaries and then another important theorem. So the examples of this one are so many, but like I'll give you a few. So let's consider the number 24. It can be written as 2, 2, 2 into 3. So you can write 2 power 3 into 3. So P1 is 2, E1 is 3, P2 is 3, E1 is 1. Similarly, we have 2, which can say 49500, some random element number. Then you can write 2 into 2 into 3 into 3 into 5 into 5 into 5. And in the end, you can write 2 power 2, 3 power 2, 5 power 3. So you can say you have P1, 2, E1, 2, P2, 3, E2, 2, E3, 5, E3, 3. This can be the example of the above theorem. And let's talk about the corollary now. The corollary is of this theorem that any integer n less than -1 has a unique factorization up to order. And just -1 multiplied with the primes. Where PIs are distant primes. I is between 1 and S, and EIs are positive integers. I is between 1 and S. Then we will give the famous theorem of Euclid. This was given by Euclid. This says there are an infinite number of primes we can actually prove this, and I want to prove it. So let's talk about its proof. So let we have a finite number of distant primes. Let P1, P2 up to Pn be a finite number of distant primes, we say it that X is the product of these primes plus 1. Now, since Pi does not divide 1, Pi does not divide X, where I is 1, 2, up to n, by fundamental theorem of arithmetic, it follows that there is some prime P such that it divides X. Thus, P is distinct from all these primes, so that we have n plus 1 distinct primes. That is, for any finite set of primes, we can always find one more. Thus, there must be an infinite number of primes. An infinite number of primes. And we will provide now the final definition of this lecture, and we end it there. We leave it there. So definition is 1.2.18. Let n be a positive number or integer, and let there is phi of n denote the number of positive integers. M such that m is less than or equal to n, and GCD of mn is 1. Then we can say phi of n is nothing but it's the order of m inside n the natural numbers, m is less than or equal to n, and GCD of mn is 1. It is the number of all those elements inside the natural numbers which are less than n, with the condition that the GCD between m and n is 1, or they are relatively prime. And we call all that number is called the Euler phi function. So examples, some small ones. Phi of 2 is 1. Phi of 3 is 2. Phi of 4 is 2. And phi of 12 is 4, because 1, 5, 7, 11 are the only positive integers less than 12 and relatively prime to 12. Remember, phi of n counts the number of relatively prime numbers to n. Okay. Then we can talk about some examples for this section and some other part. Thank you so much. Take care.